Everything you see in the universe is made of atoms, and this simple diagram unlocks their hidden structure. At the center lies the nucleus with protons and neutrons, and around it orbit the electrons, held in place by powerful forces. This is the blueprint of matter itself, the foundation of all science. This image gives us a simplified but very powerful way to understand the atomic structure, which is the foundation of all matter in the universe. At the center of the diagram, we see the nucleus, which is represented by 4 small circles tightly grouped together. 2 of them are marked with a red plus sign, which shows that they are protons, the positively charged particles of the atom. The other 2 are marked with an orange N, representing neutrons, which have no electrical charge. Protons and neutrons together are called nucleons, and they form the dense central part of the atom. Even though the nucleus is drawn large here to make it clear for students, in reality, it is extremely tiny compared to the overall size of the atom. If the whole atom were the size of a football stadium, the nucleus would be no bigger than a marble at the center. Yet, almost all the atom's mass comes from this nucleus because protons and neutrons are nearly 2,000 times heavier than electrons. The protons play a very important role because the number of protons in the nucleus tells us which element we are looking at. In this diagram, we see 2 protons, which means the atom has an atomic number of 2, identifying it as helium. The neutrons add no charge but contribute to the mass and stability of the atom. With 2 protons and 2 neutrons, the total number of particles in the nucleus, called the mass number, is 4. That is why this specific atom is known as helium-4, which is the most common isotope of helium found in nature. Without neutrons, the strong repulsion between the positively charged protons would tear the nucleus apart, but neutrons provide additional nuclear force to hold the nucleus together. Orbiting around this nucleus, we see electrons, shown as small blue dots labeled E with a negative sign. These electrons are negatively charged particles that are attracted to the positive protons in the nucleus by the electrostatic Coulomb force. The green letter F with arrows in the diagram represents this force of attraction. The arrows point inward toward the nucleus and outward toward the electrons, showing how the nucleus pulls the electrons toward itself. This attraction is what keeps the electrons bound to the atom. Without it, the electrons would simply escape into space. In this model, both electrons are drawn moving in a circular orbit around the nucleus, forming the first energy level, or shell. This is known as the Bohr model, which is not fully accurate scientifically, but is a very good way to visualize the atom for beginners. In modern physics, electrons are not thought of as little balls orbiting like planets, but rather as existing in clouds of probability called orbitals. Still, the circular orbit model gives us a way to count electrons and understand atomic stability. It is important to notice that the number of electrons is the same as the number of protons. The 2 positive charges of the protons are exactly balanced by the 2 negative charges of the electrons, giving the atom an overall charge of 0, which means the atom is electrically neutral. If 1 electron were removed, the atom would become positively charged, forming a cation, He+. If an extra electron were added, it would become negatively charged, forming an anion, He. This balance between protons and electrons is what makes atoms stable and explains why different atoms interact chemically to form compounds. This diagram also teaches us about atomic stability and chemical behavior. Helium, as shown here, has its first energy level completely filled with 2 electrons. Because of this, helium is a noble gas and is chemically inert. It does not easily react with other elements. This concept of filled shells, or the octet rule in higher shells, explains why some atoms are stable and others seek to gain, lose, or share electrons through chemical reactions. Finally, this image introduces the concept of forces inside the atom. The arrows marked with F are not just decoration, they represent the fundamental interactions holding the atom together. The electromagnetic force attracts electrons to the nucleus, the strong nuclear force keeps the nucleus from breaking apart, and the balance between these forces explains why atoms are stable structures. At the same time, it shows why protons alone could never form a stable nucleus without neutrons, because their repulsive force would be too strong. In conclusion, this single diagram shows us the most important ideas of atomic structure. The nucleus, made of protons and neutrons, the electrons arranged around it, the forces that hold them together, and the way these particles balance to form a neutral, stable atom. It is a simplified but essential picture that helps students understand how matter is built from the smallest building blocks. This image represents the structure of an atom, the fundamental building block of matter. At the very center is the nucleus, shown enlarged on the right side of the diagram. The nucleus is made up of two types of particles: protons, which carry a positive electrical charge, and neutrons, which have no charge and are neutral. The protons and neutrons are held together by the extremely powerful, strong nuclear force, which is the strongest known force in nature and prevents the positively charged protons from repelling each other. Despite being tiny in size compared to the entire atom, the nucleus contains almost the entire mass of the atom, making it dense and heavy. For perspective, if the atom were the size of a football stadium, the nucleus would be as small as a grain of rice in the center, yet it would account for nearly all the weight of that stadium-sized atom. Surrounding this dense nucleus are electrons, shown as blue dots, which are much lighter than protons and neutrons. Electrons carry a negative charge, and they are attracted to the positive charge of the nucleus. However, instead of crashing into the nucleus, electrons occupy specific energy levels or shells around it. In this diagram, the inner purple layer represents the K shell, which can hold a maximum of 2 electrons, while the outer layer is the L shell, capable of holding up to 8 electrons. This rule comes from the 2n2 formula, where n represents the shell number. Higher shells exist too, m, n, and so on, which can hold 18, 32, or even more electrons, but here only the first 2 shells are shown for simplicity. The red circular lines represent electron paths, but it's important to note that this is a simplified or Bohr model picture of the atom. In reality, electrons do not move in fixed orbits like planets around the sun. Instead, modern quantum mechanics tells us that electrons exist in regions called orbitals, which are like clouds where there is a high probability of finding an electron. These orbitals can have different shapes, spherical, dumbbell-shaped, or more complex, depending on the energy level. This uncertainty in an electron's exact location is described by the Heisenberg uncertainty principle. One of the most important features of these energy levels is that electrons can jump from one shell to another. If an electron absorbs enough energy, it can move to a higher shell. When it falls back down to a lower shell, it releases that energy in the form of light or electromagnetic radiation. This process is why every element produces its own unique spectrum of colors when heated or energized, a phenomenon that allows scientists to identify elements even in distant stars. Finally, the arrangement of electrons in the outermost shell, also called the valence shell, is what determines how an atom behaves chemically. Atoms naturally seek stability, which often means having a completely filled valence shell. If the outer shell is not full, atoms may interact with others by sharing electrons, covalent bonding, donating electrons, ionic bonding, or even loosely exchanging them, metallic bonding. This simple electron arrangement explains why some elements like helium and neon are chemically unreactive, while others like sodium and chlorine are highly reactive. In summary, this diagram shows us that the atom is mostly empty space, with a dense nucleus of protons and neutrons at the center and electrons arranged in shells around it. Though simplified, it captures the essential idea that atoms have structured energy levels, and it is this structure that explains the stability of matter, the emission of light, and the vast variety of chemical reactions that make up the material world.